Let's begin. Welcome again for, our fifth week or so. We did our first Navier Stokes solver last Thursday. We kind of hit the last few minutes. We showed in the end that it's not divergence-free. Today we'll cover that again. So I'll remind you of the algorithm we used, and we go back to the code and talk about a few little things in the code to make it run a little faster. And then we'll come back to theory and understand why it is not divergence-free. If you remember, I like to present this alternative version of the projection algorithm. We're going to call it from now on the projection method, the projection algorithm, where you split your solution into two steps. The first step is you solve the momentum equations as advection diffusion equations without the pressure. Okay? So they look like just advection minus advection plus diffusion on the right-hand side. And you store them in this provisional velocity field. We call it u tilde. So essentially, you're saying u tilde is un plus delta t times the right-hand side without the pressure. And then you take that u tilde and use it to create the true velocity field by subtracting them from each other. And the difference is a pressure gradient, which essentially is what we call the Helmholtz decomposition. So that allows you to take a non-diverging velocity field, a diverging velocity field, non-mass conserving velocity field, convert it to a mass conserving velocity field through a gradient of a scalar. With this equation, you find the equation for the scalar by taking the divergence and requiring that the new velocity field conserves mass, div u equals 0. You set that equal to 0. That's your constraint. You know this quantity, u tilde n plus 1, whatever. You know everything here for u tilde. So you can solve for p. You solve for p with this equation. You take p, you plug it back in here, and you find your velocity field. So I'm reminding you of this because I'm going to revisit it again. OK, so let's switch back to our code and remember what we did last time. OK, so let me rerun the code, restart the kernel. Let's zoom in a little bit. OK. So we'll run this again. And remember, we created these helper routines, which were super useful because we needed to do grade derivatives, first and second derivatives. They're all cell-centered, so they work nicely without having to worry about upwinding, et cetera, direction of the velocity and whatnot. We will get the opportunity to talk about upwinding when you have a varying velocity field at some point later in the course. OK, so we defined those. And then we had this Poisson equation algorithm, which was satisfying Newman conditions everywhere, except at the top wall, we set the value equal to 0 because, and again, we will visit this later when we hit iterative solvers. The Poisson equation with Newman conditions is unsolvable, undetermined, because it results in a singular matrix, the finite difference. It has non-unique solutions. You need to specify a value for it or some additional constraint. So one trick to fix this is just specify a Dirichlet condition on the pressure, say, at the top or at the bottom, whatever, and then just don't worry about it. It works just fine. OK, so that was our Gauss-Seidel algorithm. And then we declared some problem specification. If you remember, we had Lx, Ly for the driven cavity, 32 grid points in each direction. We defined our grid resolution, our top wall velocity, our viscosity, kinematic. And then we determined the stability conditions, if you recall. If you take these conditions in 2D, Courant and Reynolds in x and y, at an arbitrary grid point, you can convert those to delta t's. And that's what I have implemented here. And I want to take the minimum delta t across those two. And I picked the worst velocity in the domain, which is going to be at the top of the lid. Ideally, you want to do this stability at every grid point during your simulation. But I know in this case, there's nothing else going on. It's a confined cavity. There's no way the velocity is going to go higher than that driving lid at the top. So I choose that to dictate my stability conditions. If you're if your solution starts destabilizing, maybe take half of this time, 10% of it. Remember, those stability constraints, they don't apply to the Navier Stokes because the Navier Stokes are nonlinear. We derive them from the linear advection diffusion equations, right? So we're lucky that they work at all. So think of them as the beginning of the conversation on time step selection. Okay, they're a good starting point. They provide an upper bound, if you think about it. So you can go lower and lower to make it stable. You will see in your project, you might get some unstable solutions. You will have to reduce your delta T as you get more nonlinear effects, okay? As you quite laminar, nice diffusion equation, and that's why those time steps work for such low Reynolds number. The Reynolds number here was like 20, right? So that's a very, very laminar flow, if that makes sense. And then we did our time advance. You all, I'm assuming, have this code at this time, where we set the boundary conditions. You can choose to put the boundary conditions at the beginning of the time step or at the end of the time step. It should be consistent. I like to put it at the beginning of the time step because if I'm doing something wrong in the solution and I'm messing with the boundary conditions, when I plot the solution, the boundary conditions are going to change, and then I'll know something happened at the boundary condition. If everything is correct, the boundary conditions should not be touched. Okay, even when you do the final time update with the pressure gradient, this pressure gradient should be 0 at the boundary. So it would not, and this right-hand side would be 0 at the boundary. So U at the boundary equal U at the boundary. U new is equal to U old at the boundary. It's not going to affect it. Okay, so we did all of this, and so let me run it, and we run it. Of course, it's going to crash because. Okay, so let's run it again. T is not defined. Oh yeah, so time equals 0, and I'm going to run 100 time steps, and it's pretty slow. Okay, it's very slow because of that for loop. And yay, we have a solution. It looks like, yeah, it's doing what it's supposed to do. The color here corresponds to, so PLT dot color bar. Let's see, it's going to give me a different color bar. And let's say CMAP equal jet. So I want it to give me the color bar of the jet. Okay, hold on. Okay, there you go. So red is high and blue is low. And you can see that, yeah, okay, so there's like 1.05. There's some error going on here, and that's because our solution is not 100% mass conserving. We're going to see some departure from what we expect the max velocities to be, etc. But still, it looks much better than when we didn't have the pressure gradient. So indeed, the lid is moving. So the axial velocity, this is plotting speed, okay? Colored by speed. So I computed the speed here. So red is high, blue is low. So indeed, the speed here is inheriting the speed of the lid, okay? And then it kind of diffuses slowly, and then we should expect you start seeing this flow, how it's spinning, because it's trying to move over there. Because of that pressure gradient, because of mass conservation, it has to turn. Then it hits the bottom, it has to turn, and it creates this large vortex in the middle. Okay? Now, we expect this as the lid moves faster, as we increase our Reynolds number, that primary vortex is going to move a little bit over here. And you will see with larger Reynolds numbers, you're going to have a recirculation zone here, another one over there. So that'll be part of your project investigation. But I wanted to show you this. And so let's run another 100 time steps, see if it changes anything. Again, it's pretty slow, and that is annoying. We will, on purpose, okay, because later I want to teach you iterative solvers, and we'll solve this in a fraction of a second, okay? And you see the flow starts developing more and more. I do have, however, for you, a better and a faster iterative solver, which I'm going to present to you here. I'll send it over Canvas, put it in a Jupyter notebook for you. So I have another Poisson solver, although it requires more iterations to converge, but it's vectorized using Python slicing. So if you were to take the Jacobi iterative solver, where the new iteration depends only on the old iteration, you can essentially vectorize everything using old values. So you see here, I'm not doing a for loop anymore. I'm just saying the new value of the pressure is equal to whatever the Jacobi solver is doing. You can look at the formula for Jacobi. This is, pi plus 1 plus pi minus 1, whatever that formula is for the Jacobi solver. If you vectorize it this way, although it takes more iteration than Gauss-Seidel, it's vectorized using built-in Python routines, those slicing, and it will still be faster overall. Okay, so let me show you how this one is going to work. So this will be our Poisson vectorized, let's say. Okay, and this is our old Poisson solver with these nasty loops. Although it takes less iterations to converge, the other one is still faster. So let me show you where is Poisson vectorized, and it's already done. Look at that. So I'm gonna run it. It's already done. See how fast it is? It's about 10x faster just because of that vectorization. Okay. So I will send this over Canvas right now. Okay, let me send it over Canvas. One second. I always prefer my wall time to be faster. I don't care if it's taking 1,000 more iterations. If in the end it's faster, that's the bottom line, right? So we will take that as a victory. Let me first. So I'll just send this as an announcement on Canvas. If you have your Canvas login, and you can just copy and paste this into your code. It takes the same function signature as the other one. So you just have to change the name or copy paste the whatever is inside it. Okay. Vectorized Poisson solver Jacobi. So you cannot do this vectorization with the, with the Gauss-Seidel or the SOR. They're not as clean as this one. So I sent the announcement. Feel free to just copy and paste it. Now, here I'm defaulting to a tolerance of 10 to the minus 3 and a maximum number of iterations of 25. You might want to increase that to 50 if you want, and maybe set the tolerance at 10 to the minus 5. Now, what will this tolerance imply eventually on your solution? This will be exactly proportional to the error in your dilatation. So you solve the problem, you use this Poisson solver to compute the pressure, you update the velocities, then you go and compute div u. What is the error in div u? It's going to be exactly that norm, that tolerance. Now for our scheme here, div u is on the order 1 because that scheme doesn't work for other reasons. But once we get to the finite volume method, where we will satisfy mass conservation discretely, you will notice that div u at every point will be proportional to that tolerance that you choose here, or at least this would be the worst error. Okay, so this is strictly tied into the dilatation, the error in your dilatation, because remember that Poisson equation is obtained by taking the divergence of your discrete equation, right? And so, however well you solve that Poisson system is going to translate directly to your dilatation in your velocity field. Okay. All right, so now we have a vectorized version. If you got that announcement, please put it in, and you can delete this or comment out this older one. We don't need it anymore. And then you could be using this, so we can increase, let's say, our wall velocity. Let's go to a Reynolds of 200, Okay, again, it's pretty fast. Now, see, with higher Reynolds number, you're going to see that primary vortex move a little to the right. So this is a highly unsteady problem, so you need to run it for much longer residence times. I would say at least, 10 times. Well, you take the speed of the lid and make sure, like think of a velocity particle, of a fluid particle at the lid, moving at that speed. How much time will it take to circulate the entire cavity, right? If the cavity has a perimeter of, let's say, 4 meters, right, and you're driving at 10 meters per second or 1 meter per second, so you need 4 seconds for 1 meter per second, or half a second for 10 meters per second, and so on. So that will help you choose your end time, simulation time. But look at this. This is pretty cool. You can do an unsteady calculation here, and you will see how that vortex is evolving. I'm not going to do an animation right now. It will take a long time, but I will ask you to do that in your project. It will look pretty nice. And I don't know if you're trying this on your codes right now. Yeah, my code is working? Staying in the center. Did you change your speed, your cavity speed? Yeah. So change that, get that faster Poisson solve, put it in, and see what happens. OK. Now, give you a minute to catch up. Okay. And you can, this is like minimalist visualization. You can do some really nice visualizations. You can do a stream plot as well, lt.stream plot, and you can say this is x, y, and then uv, and then density equal 5, let's say. And you can do some really nice plots for the driven cavity. Color bar, density equals 0.1, let's say, 0.5. OK, so you can start seeing the streamlines of the flow as the flow is evolving. OK?
I didn't finish in like a second.
Pardon me?
I just finished like that.
You right?
Yeah.
That's pretty cool. Yeah. So you can add the stream plot and change the color, et cetera, and and you can see some beautiful visualization going on with the cavity. You can animate all of that. Okay. It's called stream plot. This is, again, minimalist visualization. You would want to customize this so they look pretty and they're not like blue on blue, et cetera, right? So, play around with the color, line width, et cetera. Visualization is very important. I think we will talk about visualization later in the course. But for now, try to produce some nice, good-looking visualization. OK. So now I want to get to the elephant in the room and say, well, the primary difference between Navier Stokes and advection diffusion was mass conservation. And so we spent weeks talking and to get to the algorithm. So let's try to see if we're truly mass conserving. We're not. We showed that last week. So let's see it again. And if you plot your dilatation, you're going to see, like, unfortunately, it is not divergence free. Look at these points over here. Even if one point is not mass conserving, your solution is not mass conserving, period. You can't not conserve mass at one point, but say otherwise. It's like, OK. It's not good. This is not working. So what the heck? Am I teach you something, incorrect? No. This is historically what happened. OK. So I want to do a little trick for you now, and then come back to theory. But I first want to remind you of the scheme we're doing. OK. So again, I want to remind you again one more time of this scheme. So we did not explicitly compute this u tilde. I want to add it manually in the code. So u tilde is essentially un, right, minus delta t or plus delta t times advection plus diffusion, right? So my u tilde is really this entire guy over here. Actually, yep, this is it. I already have it. ut, right? U tilde and v tilde. So those are my tilted velocities. And for the pressure right-hand side, instead of doing this, we could have done just simply, this is what we left off, I think, last time. U tilde and v tilde dx dy over delta t, right? That's what our formula is saying here. That the Poisson right-hand side is this guy, div u tilde over delta t. Okay, so that's exactly, those are identical statements. Those two lines are identical, okay? Those two lines are identical. I'm just changing it for consistency, okay? So I'll run it again, and you'll see, indeed, we are getting that correct solution, or what we had before. Okay, and we're still not divergence-free. Okay, now I want to do something to make div u equal to 0. And I'm going to do div u, let me buffer, div u is equal to div u tilde, okay, div u tilde dx dy plus Laplacian of p dx dy, okay, or minus plus, yep. So if we think about this algorithm, yeah, so I'm trying to compute now div u tilde minus del squared p manually. Over here, what we did, we updated the velocities with the pressure gradient, and then we took their divergence. Here, I want to take the divergence of u tilde and manually subtract from it the Laplacian. Okay, so I'm essentially computing this div u tilde minus delta t del squared p to see if it's what it's going to give me a div u, another div u. Okay, div u other. Okay, plt.im show div u plt.color bar. Okay, now it's on the order of that tolerance that I showed you up there, right? 10 to the minus 5. Okay, so if we shrink that tolerance, so as far as I'm concerned, this is divergence free. So I'm going to go to like minus 12 and do 200 iterations over here so that I really drive this down to 0. Okay, so okay, there's something minus dt times Laplacian p. Yeah, so this is by all means a divergence-free. Hold on, 1 second. 1 second. Give me a second. So what happened here? What's going on? Why is this giving me? I mean, you think like this is the same formula, right? It's Laplacian div u tilde minus dt times Laplacian, same thing as we had before. So why is it giving me something different? We have to go back to theory to understand what's going on. And I actually, when I derived this algorithm, I made a mistake on purpose that passed through everyone's radar. Okay, that passed through everyone's radar. So let's revisit and understand what's going on. So let's understand what's going on. So indeed, this scheme doesn't work. Okay, it is not divergence free, and we will learn that any fix will lead to what we call even-odd decoupling or checkerboarding problem. I will demonstrate that to you. You will have even points on the grid coupled together. Odd points, they belong to a different solution. It's like you're solving two different problems on the same grid. It will lead to unphysical solutions in the pressure. They become oscillatory, and unphysical solutions in the velocity. And it also violates a theorem in math called the div stability condition. I don't even understand it, but I know the result for that theorem. And so just because we're using cell-centered finite difference schemes. So we're going to go through those. But first, I want to explain to you why this is not divergence-free. So one thing we could do is we have the formula for the Poisson equation, the formula for the pressure equation. It tells us that del squared P equal div u tilde n plus 1 over delta T, right? And so we can check mathematically, analytically, to see if we take the divergence of this, to see if we indeed satisfy div u equals 0. So if I were to take the divergence of this, okay, now notice what I'm putting here. This divergence operator is based on the grid spacing, is based on delta x or delta y. Okay, so delta x and delta y. Okay, and div, same here. This is based on h. This is based on h. But this term is what matters. Okay, so I'm taking div u tilde, div u n plus 1. This is our solution, right? And this is div u tilde. And now we want to check that indeed, if we solve the pressure correctly, those two terms should cancel out. However, the equation that we solved is del squared P based on H, not div grad P based on H. If you see where I'm going, this is equal to this only if and only if div grad is equal to del squared. The divergence, the discrete divergence applied to the discrete gradient. In the previous slides, I automatically, this was my sleight of hand. I was like, yeah, div h, this is Laplacian. Everybody agreed. And I was laughing on the inside, right? Because nobody, you don't see that until you see it, right? So now you see if this guy, delta t times div grad p, if it's equal to div u tilde over delta t, then delta t will cancel out, div u tilde will cancel out, and you'll get div u equals 0. Okay? So now the question is, div u n plus 1 is 0 if this symbol is if and only if div grad p is indeed equal to del squared p. Okay, so let's see. Let's check. This is our grid. Okay? And we'll do it in 1D just for simplicity. So del squared P is our standard second difference operator, central second derivative operator. Pi plus 1 minus 2pi plus pi minus 1 over delta x squared. Okay? But what about div grad? If you were truthful to the math, which the code is doing, because the code is doing u is equal u tilde minus delta t grad p, and then you take div of that, it makes it div grad p. So what is div grad p? Div grad p is the divergence of the gradient, which is grad pi plus 1 minus grad pi minus 1 over 2 delta x. And you build that up. Turns out that div grad p is pi plus 2 minus 2pi plus pi minus 2 over 4 delta x squared, which is not equal to del squared p. So del squared p is coupling points I plus 1, and I minus 1. But div grad p is coupling points I plus 2, I minus 2. It's skipping every other point. Same thing for this guy. Div grad p over here is coupling this guy and that guy. Okay? And so they're not equal. And that's why we don't have div u equal to 0, because the equation we solved is not the equation we were supposed to solve. We solved del squared p equal div u tilde over delta t, not div grad p equal div u tilde over delta t. Does that make sense? So this is the inconsistency. You cannot assume continuous math on a discrete grid. Continuous, you could say, div grad is indeed del squared. Yeah. And that's the mistake we did here. We assumed that div grad is del squared, but it's not del squared. It's something different. It's a wider stencil. It's a different del squared. It's a del squared based on twice the spacing. Okay? So then you could argue, well, Professor Saad, why don't we solve this equation for the pressure instead of that one? Okay? You can do that. You'll get, if you're lucky, you'll get divergence free. The problem is, when you operate with a wide stencil like this one, So this should be del squared 2h here, 2h, sorry. If you do this one, it will lead to what we call the even-odd decoupling problem. Because of that stencil is wide, you're only coupling points I plus 2, and I minus 2. And the other points are coupled to each other. So you have two grids, two different grids operating at two different solutions. You're lucky if they have the same condition, but in general, they will not. And that would lead to highly oscillatory solutions. So let me give you an example. So let's say we want to solve this 1D Poisson equation on this periodic domain. So we know now periodicity. We know how it works. This point should be P2, this point P3, etc. And we want to solve this Poisson equation. We did something similar at the beginning of the semester. But I want to use a wide stencil to solve this equation. Okay, it's just a simple Poisson equation with a source term. I know the exact solution for this one. It can easily be integrated. Okay, so let's write the discrete equation. At point 1, you get P2 minus 2P1 plus Pn minus 2 equal 4 delta x squared times B1, whatever. And then at point 2, you get P4 minus 2P2 plus Pn minus 1. You see how you're skipping every other point. And dot, 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 you build your system of equations. And what happens, you get a matrix where this row is not coupled to this row. So this equation is not coupled to this equation anymore. Okay, and this equation is not coupled to this one. This equation is coupled to this, is coupled to this. So you're skipping one equation at a time. And what happens when you solve this system, you will get two different solutions on the grid. The even points will have one solution. The odd points are going to have another one. It looks the same, but it's going to be shifted. Now, from the perspective of the fluid flow, imagine you're doing this on the pressure. The pressure is going to vary widely from one point to another. It's going to look like high oscillations, and the pressure is going to crash your solution. Okay? That's because of this even-odd decoupling. So here's another perspective at it. If you were to rearrange the equations here and put P1, P3, P5, or the odd points and the even points together, then they become coupled again, but you have two different systems of equations that you are solving, essentially. It's like you completely decoupled the problem. The even points have a solution. The odd points have a solution. You're lucky if they fit on top of each other. In general, they will not. And when they will not, this will be perceived by your code as a very highly oscillatory pressure field, which will crash your solution, right? So imagine this is being a pressure field on your solution. It's unphysical, unrealistic. OK, the pressure checkerboarding problem. So I listed 4 issues with this. If we were to use the wide stencil to solve the Poisson equation, we have all of these issues, the even-odd decoupling, the pressure checkerboarding. We do this next. I'm going to take the 1D equivalent to the momentum equations. Okay, so it's got nonlinear advection, a pressure gradient, and diffusion. And consider this 1D situation. Suppose this is your initial condition. For some crazy reason, you want to put this initial condition. Okay, and you should be, your code should be your solution, your numerical solution, if done correctly, should be able to handle slightly atypical initial conditions. So imagine you have this initial condition. U is equal to 1 everywhere. This is not unusual. But P, just on purpose, for the sake of it, you make it highly oscillatory. 2, 1, 2, 1, 2, 1, 2, 1, just on purpose. Now, the reason I'm doing this is because I want to couple these points together, okay, and the even points together and the odd points together. Okay, here's what will happen. Let's say we want to discretize this equation. The advection term is 0 because U is 1 everywhere. So I plus 1 minus I minus 1 instead over 2 delta x is 0. The diffusion term is 0 because U is 1 everywhere. And the pressure gradient is 0. Despite the fact that it's highly oscillatory. So if all of those terms are 0, this means your solution is not going to, it's just going to stay the same. Yet you have a highly oscillatory pressure field. So I'm posing here the opposite problem. If you have a highly oscillatory velocity field and a constant velocity field, highly oscillatory pressure field, the flow is not going to sense it. It's not going to feel it because of that centered differencing. Although you would expect here the flow to go berserk, like this is a highly oscillatory field, is going to create all sorts of waves, is going to change, to create a lot of dynamics. Yet your numerical solution will say un plus 1 equal un for all times. It's not going to move, which is unphysical. Okay? Same thing with velocity. Again, consider this situation where now your velocity is highly oscillatory. Okay, your velocity field is highly oscillatory. So you would expect that your pressure to have also to respond to that. Yet, what happens is that with the conditions that we want to solve, because the Poisson equation, d2p by dx squared is div u tilde, and div u tilde is 0 because 2 minus 2 is 0, 1 minus 1 is 0, 2 minus 2 is 0, 1 minus 1. Remember, we are centered, right? We're coupling every other point. It's not going to sense that. So despite the fact that we have a highly oscillatory velocity field, you're going to get a constant pressure field in this case, which is also unphysical. So these are really issues with the finite difference centered scheme, okay? Whether it's coming from div grad or just even the standard derivatives. And finally, the div stability condition. That's like the worst. That's the least anyone could understand. There's a theorem in finite element analysis known as the Ladijenskaya-Babushka-Bredzi condition, or LBB, also called the div stability condition, div for divergence stability. It says that the combination of centered finite difference scheme and co-located grid does not satisfy the div stability condition. So what's a co-located grid? When we put all our variables at the same point, P, U, and V, and temperature, everything at the same point. The way to fix this is not to put them on the same grid. So I'm starting to hint to you what we're going to do next, okay? The div stability condition needs to be satisfied to have a stable numerical solution. Second, it is necessary to use different meshes or different order interpolants to break that symmetry from the centered schemes. So like use forward differencing on advection, backward differencing on the Laplacian, try to come up with crazy different combinations or higher order just to try to break that, okay? If you're using a finite difference scheme and co-located. Now, modification of the continuity equation circumvents this condition. So that means using artificial compressibility, which we're not gonna cover here. But like this theorem is from 1989, even earlier. I don't know if I have the reference for that paper. Okay. So what is the remedy? The remedy is what we call the staggered grid. Who's heard of that word? Staggered grid? Staggered grid? Okay. The remedy is the staggered grid. Ingenious method developed, created in the 50s, okay? And the motivation is, okay, we're going to keep our centered discretization. It's second order. We like it. It's simple. But we're going to place the variables at different locations on the grid so that we can trick the code and the math to give us a div grad equal Laplacian. Okay, we're going to move things around. So here's the, I'm just going to give you a taste of it. We'll dig into it starting Thursday. We place the pressures in all scalars. This is one version of it. You place all the scalars, temperature, enthalpy, energy, species, and the pressure, all scalars at the cell centers. And you place the velocities at the faces. So now we no longer have a grid point only, like we did before. With finite difference schemes, we had just these blue grid points. Now we're saying we're going to create another grid halfway between those grid points or some way between those grid points. And we no longer just have a grid. We actually have a control volume, a small volume over here, where this volume has faces on it, and we're going to place the velocities on the faces. Now see what happens when you do this. So if we were placing the velocities this way, then the condition on continuity, So these would be our equations in 1D for simplicity. The du by dx equals 0, and the 1D momentum equation, okay? So that's div u equals 0, and momentum, advection, diffusion, and pressure, okay? So let's see how this discretization works. For the convection term, okay, you're still doing, at point I, you can still do ui plus 1 minus ui minus 1, okay, over 2 delta x, okay? That's fine. That will work, okay? For the second derivative for the diffusion term on momentum, you're doing ui plus 1 minus 2 ui plus ui minus 1 over delta x squared. Okay, good. Still works the same. Now the pressure. Now remember, the pressure belongs to the velocity equation. So the pressure gradient lives where the velocity lives. If you think about that, where are you placing your gradients? You need to place them to the equations they belong. The pressure gradient dp by dx belongs to ui. Okay, so we can evaluate the pressure gradient as pi minus 1 over delta x. Now notice what happened here. Previously we had a wider stencil, pi plus 1 minus pi minus 1 over 2 delta x. Now we shrunk that stencil. It's delta x apart. Okay, it's still between two neighboring points, but even the indexing changed. Now you have pi and pi minus 1, not pi plus 1. Okay, so now what happens when you take the divergence of the pressure? Okay, so this is our u tilde. Now what happens when you take the divergence of the pressure? You take the derivative of dp by dx. Then you're going to bring in this point. You get this gradient minus this gradient, right? pi plus 1 minus pi over delta x, and pi minus 1 over delta x. You combine them, and bam, you get the div grad equal to the true Laplacian that we care about. Okay? This is nothing more than the derivative of this. So this is the derivative of this. And it's this gradient minus this gradient over 2 delta x. Okay? Oh, sorry, over delta x. Okay, so now here's what happens to show you that the divergence is indeed 0. So I'm going to check if the divergence of my new velocity is 0, d by dx of u at n plus 1. It's d by dx of u tilde. Okay, we got that. We figured that out. But this one, d by dx of dp by dx, okay, is this equal to that one? Yes, it is exactly equal to that one. Okay, so when you do this operation, this derivative of dp by dx, you get the gradient here minus the gradient here over that spacing, and then you get the correct velocity form, okay? So you get that same value over there. And indeed, your dilatation will be identically 0 at every point. This simple thought experiment actually leads us to what we call the finite volume method. Because those little cells that you saw, those are going to be our control volumes. We're going to have velocities coming in and out of them, and they're going to change the content of the control volume. Okay? We will do the control volume on Thursday. So that's it for today, but I want to talk about the term project. So we still have about 20 minutes, 30 minutes. So I'll talk about the term project, the first project. I'm hoping to do more than one. Last time we did 3 projects. Probably this year, this summer, we will do 2 because it's a shorter term. Okay? It will take a minute to absorb everything I said. And it's going to get harder now because things are going to get really complex. We're going to have to keep track of 4 grids and all of that. But it works beautifully. Once you figure it out, it just works beautifully. No issues. You get discrete zero divergence, machine precision divergence. It's very beautiful. Okay? Revisit the video if you want and kind of spend some time thinking about, do the math by hand, challenge yourself, challenge what I have in the slides. Okay, and I've been getting a lot of really nice questions over Canvas, so we've been handling them. And you know, it sheds some fun light into CFD. Okay, so let me show you the what I'm thinking about the project this year. It's similar to the project last time, but quite different. Okay, so let's see. Oops, no information. Okay, so project 1 is going to be a driven cavity, which we did in class, right? But we're going to make that cavity heated, okay? So I'm going to insulate it on all sides except on the left side. Okay, we're going to specify a temperature, a wall temperature on the side, and we're still going to drive the cavity from the top. Okay, so there's motion of the fluid that's causing the fluid to move this way because of the cavity, but also this cavity is heated, and we're going to allow buoyancy effects to take place. So if you heat a wall, you notice that the hot air is going to go up, right? So the hot air in this cavity, or the hot fluid, is also going to move up, which is going to contribute to that motion of the cavity. It's going to augment it or not affect it. But there's also diffusion of heat, not by the motion of the fluid, just diffusion by sheer fact of viscous and thermal conductivity effects of the fluid, right? So you heat a wall, even if there's no motion of the fluid, you might get just diffusion just because of molecular communication, okay? So just by sheer diffusion. So it's an interesting problem, but you will have to do a few things. So you will need to modify the Navier Stokes equations by adding one more term to the y momentum equation. We call that a Boussinesq approximation, okay? So it looks like this. It's a minus beta delta T, and I'll explain what T0 is, this initial temperature of the gas inside the cavity, times the gravity. So you see this is a gravity-driven flow, buoyancy-driven, because of gravity. Colder air is going to sink down, it's going to push the hot air up, or the hot fluid up. Okay, so you will need to add this term into the y momentum equation, okay? And you will need to add, to solve one additional equation, which is this guy, dt, the energy equation, as in terms of temperature, okay? And you know what? We know how to do advection diffusion, okay? However, now, your velocity, where is this coming from? Your Navier Stokes. It's not a constant. We used to use a constant when we did it in class. No, now you need to couple it with Navier Stokes. So you solve the Navier Stokes, and you take that velocity. You need to do the discretization. You do everything by hand to understand what you're doing. You take the velocity from your Navier Stokes solution. You plug it in here. You solve. Now that temperature, guess what, is also going to go into that source term here. So the temperature, the fluid is driving the temperature equation, and the temperature is driving the fluid equation as well. So this will go into the y velocity. It's going to cause that v velocity to go, higher, right? It's going to be a positive source term, okay? And not only that, so I will ask you to do it over different densities, viscosities, different sizes of the cavity, different wall velocities, different thermal conductivities. So that becomes a nightmare. So what I will ask you to do is to non-dimensionalize the problem. And you will notice that this entire problem with the whatever 6 parameters can be done only with 3 parameters: the Reynolds number, the Richardson number, and the Prandtl number. And you will have to derive those, rewrite the equations in dimensionless form, discretize the dimensionless equations, and use the code that we did in class. And you need to just add a temperature equation and a source term to it, really. There's nothing much to add to the code, okay? But you'll have to do a few things. Your time step stability needs to be redone in terms of the dimensionless solution, so that you can determine your stability conditions based on the normalization. So I explain everything here. So the equations should be solved in dimensionless form. For temperature, you use this normalization. So it's just simple algebraic math. It's not that tedious. And you normalize the velocities by the wall velocity, the time by L over U wall. L is the length of the cavity, which is aspect ratio 1 by definition. All distances are normalized by the length of the cavity. And the pressure is normalized by U squared, and this is theta. So you take those, you change all the equations, and you write them in terms of U tilde and P tilde and theta, okay? So you'll have non-dimensional equations. What you will get, you'll see a Reynolds number, a Prandtl number, and a Richardson number show up. Now, if you don't know what if you haven't seen what dimensionless numbers are, I'm going to add a little blurb here at the bottom to kind of help you think about them. The Reynolds number essentially measures, it's a measure of inertia versus viscosity. The Prandtl number is a measure of viscous diffusion from the flow versus thermal diffusion. And the Richardson number is a measure of buoyancy effects. So the higher the Richardson number, the faster, the stronger your convection is happening at the wall, at the heated wall. And you will vary those different numbers. So instead of thinking, like, oh, I'm going to vary U, density, viscosity, thermal conductivity, heat capacity, and all of those things, just vary those three numbers. And, so that gives you a coverage of the entire space of problems. You will have to rederive your stability conditions. So you just need to normalize also your stability conditions. And they will all become a function of Reynolds number, Prandtl number, and Richardson is not going to show up because it's a source term. Our stability conditions did not include source terms there, okay? Now, the code being a finite difference code is going to cause some problems for you. So you might see some instability. That's okay, just report it, okay? And all I'm asking of you is to give me a presentation about what you did, okay? So show the derivation, how you did the derivation, how you solved the problem, okay? And just show me some results saying, okay, we fixed the Prandtl number and Richardson and varied the Reynolds number. Next, we're going to fix Prandtl and Reynolds, we're going to vary Richardson. We're going to fix next Richardson and Reynolds and vary the Prandtl number and see kind of the sensitivity to those different three parameters, right? I will also ask you to, so once you get the code running before you add heat transfer, is to just validate your code by comparing to an experimental data set for the driven cavity. It's actually a numerical data set. So there's a paper by Guy et al., pretty old paper. They have some data for the velocity along the center line. So you run your calculation, okay, for Reynolds equal 100. If you normalize your equations and write your code in dimensionless form, all you have to do is say Reynolds 100 run. Everything is sorted out. You get the results. Plot your solution on top of the other solution. Refine your grid a little bit. And then run again until you see like, yep, you're not seeing much change with the other solution by Guy et al. So that would be your first step before heat transfer. And then the heat transfer, and it's open-ended. It's up to you to tell me what you discover. You might come up with a new idea about kind of understanding like how heat transfer affects. Maybe you want to put, what happens if you put the heating on the other wall? So the fluid is trying to come down, and the convection is trying to go against it, right? So what's going to happen to the flow? It's going to split, right? So open-ended, up to you. It's your code. It's pretty fast. You can run it decently. And I will give you also some guideline on how to choose your grid resolution. Because I expect that your code, because it's finite difference and it's not mass conserving, you might see some issues in some cases. And that's okay. That's okay. This is not this is an open topic, a research topic. You're going to stand up, you're going to talk to us, you're going to say, oh yeah, this is right, oh, we faced this problem, here's how you fix it, etc. Okay? So just the opportunity to do the work, try to think about it critically and report your results is what I'm looking for. Okay? No report, just like a 5-10 minute presentation, some plots and some animations would be great. Okay? Does that work? Yeah, you have the lid-driven cavity code. So, you're like 90% there. You have to clean it up a little bit because you need to write it in dimensionless form. And in fact, with dimensionless form, it's much easier, but you need to do the math. So it will force you to redo the math that you just saw on the slides, okay? And we'll be here to work with you on it. I'll release this project by Thursday just to kind of add some more text to it and make sure you have all the information you need. And that will be our first project, maybe 2 to 3 weeks. And by that time, we'll do our second project where we learn the finite volume method. And then we will do flow, maybe flow over an object, like flow over the U. We'll put the U symbol and see some vortex shedding behind it, et cetera, right? Anyway, we'll think about that later. But yeah, this is our project, my project. I don't know. I think it's simple enough to give you, to put things in perspective, and not to brag, but just as a matter of fact. many CFD courses, unfortunately, at the graduate level, you have to wait until the end of the semester, and you'd be lucky if you do the driven cavity together in class, and that's it. Here you're doing driven cavity plus conjugate heat transfer with it, and buoyancy, okay, understanding the problem. We're not doing it 100% right because of the finite difference, but it's still an okay solution, okay? Because finite volume is only going to change a few things, and then you can update your code and make it fully divergence-free, okay? But there's a lot to learn. You're going to see like, oh, why is my solution becoming oscillatory? My time step is stable. Well, you know what? You might be hitting turbulence, which your stability conditions are not going to account for, because those are through source terms and more nonlinearity. Our stability conditions are derived for the linear regime, okay? So you might get an unstable solution, and that's okay. You can sleep at night. Don't worry about it, but try to reason about it. Try to think about it. Think, oh, diffusion should diffuse things. Central schemes are going to be oscillatory. You know, we're going to see some oscillations. Finite difference not conserving mass, okay? All right? Does that sound good? Yeah? If you have ideas for other projects, let me know. Usually, I leave the final project for you to choose, your own final project. But I don't know if we will have time this semester because it's shorter. So we might just do one more project and then, you know, be done with it. But I think this is a pretty decent problem to look at. You know, it's got good. Now, for those of you who have not done non-dimensionalization before, we're happy to help you. It's very easy. It's not rocket science, okay? And she just gives a universal character to the equations. So you don't have to think anymore about specific parameters like density, viscosity, thermal conductivity. You just think in terms Reynolds number, Richardson, and Prandtl, okay? Then you realize, oh, as the Prandtl numbers shrinks, do I have more diffusion or less diffusion, right? If Richardson number goes up, I'm going to have more or less this free convection, etc.